Hello, everyone. This video is to work through a few example problems for you that are the kinds of problems you might be asked to do when we're looking at finding proportions of populations that have larger than or smaller than or in between certain value for X. Now, we've been doing this and for just using the normal distribution, but what's important about the step that we're doing using the central limit theorem is it's going to help us transition from needing to know mu, the true population mean, and needing to know sigma, the true population standard deviation, right? So in the real world, we don't know these, and we can't know them. So if we're going to do any actual practical statistical tests, we need to have some methods that are going to allow us to use an actual mean of our sample from the population and the standard deviation of the sample from our population. All right, so it turned out that a critical step in making this connection was the derivation of what's called the central limit theorem. And the idea of it is that if you take many samples from the population and you find the mean of the sampling distribution and you find the standard deviation of the sampling distribution, then it tells us something about the relationship between the sample and the population. And that's what we're trying to do with induction and inference. Okay. So for the mean of the population, the central limit theorem, if that's the variable we're interested in, the central limit theorem tells us what's shown on this slide. So for a population with mean mu and standard deviation sigma, the sampling distribution of sample means will have mean mu, which is the same as the population mean. Okay. And it'll have standard deviation sigma divided by root n. Right. So in this case, we still need to know sigma. But then we're going to modify it based on the sample size. Okay, so this sigma over root n, the practical implication of it in terms of solving problems is that when we're given data where we have a sample that's taken and we'll have a sample size given, we still need to know the standard deviation from the population, but that's temporary. We'll get to how we're going to work our way around that in a couple of weeks. So we're just going to replace the sigma with sigma divided by root n. All right, so let's look at a couple examples of what we're going to do. Excuse me. If we're in this situation. All right, so this is just a visual showing these distributions. So how are we going to get this sampling distribution? We have a population, its mean of something is 25. We're going to take many samples of the same size. All right, so the sample size is going to be the size of the samples that we took. Excuse me. On a Sunday afternoon here making this recording, and I might need to take a nap after it. All right, so what we're going to get is a distribution of all of these means that we got from our samples. And this distribution is going to have mean mu, and its standard deviation is going to be sigma over root n. All right. What does that look like? We're actually looking at data. So our population is going to have this kind of wider normal curve. And its mean is 25. And suppose we know that its standard deviation is 7. If we take these means of samples with 10 subjects in them, then the relationship between the sampling distribution and the population distribution is that the means should be the same. And the standard deviation is going to be skinnier, it's going to be less. And exactly how much less it's going to be depends on sample size. So in order to find the standard deviation of the sampling distribution of the sample means, we're just going to take sigma and divide by square root of the sample size. Okay, so as the sample size increases, the standard deviation of the sampling distribution of sample means is going to get smaller. So this is one of the reasons that having a large sample size is good, is because it's going to decrease the standard deviation of our distribution, and that's going to make it easier to tell the difference between samples that might have different means. So I'm going to just work a couple sample problems for you. There's not really too much to learn here, except when you're given a problem that has a sample size in it, you need to use it. Okay, you need to use it. So we're going to have a version of our way to solve normal distribution problems, where instead of finding z by just using x minus mu or sigma, if we have a sample described in problem with a little n sample size, we're going to modify this equation, and it's just going to be z equals x minus mu over sigma divided by root n. All right, so we're going to have these two different scenarios. The questions otherwise are going to look basically the same. Find the proportion of individuals with X greater than 80 out of this population, right? And then we're going to need to find the Z, but we're going to use the sample size by modifying this in the denominator, take into account that we know when we're taking samples that our standard deviation is going to be skinnier. Okay, so I'm going to do one kind of preliminary demonstration for you. Your worksheet is also going to demonstrate this as well, because you'll actually have some a simulation to use that's going to help you understand what the sampling distribution is, where it comes from. You'll actually get to sort of see it getting formed. All right, so suppose we have a situation where we have canned anchovy fillets, and we are getting these from a particular cannery processor that has anchovies that they harvest that have a true mean mu of 75 millimeters for these fillets and a true population sigma of 12 millimeters. Right, and they're going to put these fish into 3 different products. They're going to have home cans, sort of normal little cans, and then there's going to be 9 fish or fillets in these. We're going to have bulk cans, bigger ones, and there's going to be 144 fillets in those. And then there's industrial cans. So these ones, they're going to go to, like the frozen pizza manufacturers. They're not going to home cooks. And we're going to have 400 anchovy fillets in those. Okay, so each can, we can take it kind of as a sample. And the cans have different sample sizes. And so we're going to look and see what our distributions look like based on the different number of samples. So if we say that this is going to be true for our population, it's like saying the sample size is 1. Right. So we're not really taking a sample at all, but the way the formula works, right? So our standard deviation of our sampling distribution, the distribution of the x bars, is going to equal sigma over root n. Right. And so what I'm doing right now, we're just going to be finding the sigma over root n. Right. And so when you use that equation to find little z, you're going to be substituting in this sigma divided by root n. So if we have, we want to find the mean and standard deviations of the sampling distributions for our cans of each of these sizes. For our population, and then also for these 3 different sizes. Okay, so if I'm drawing a histogram of my population distribution, it's going to have mu equals 75, and its standard deviation is 12. And so over here at 80, 88, right? And then 75 minus 12, which is 63. Uh, that's going to be its standard deviation and its mean. All right, so that's our population, right? Equivalent to our sample size being 1. We're going to take 12 and we're going to divide it by the square root of 1, which is 1. All right, so for our home cans with n equals 9, we're going to have 12 over root 9, which equals 4 as the standard deviation. So if we're going to draw our normal curve, oops, that's terrible. It's going to have the same mean, 75, but instead of 12, it's going to have 4 for its standard deviation. So we're only out here 80 and 71. 39 and 71 on each side. All right, so it's skinnier, so it's going to be a little taller. All right. So notice if we were going to find an area under the curve that was, less than 70, the area that's in the tail is going to be smaller when we go to this sampling distribution. So that means this probability that we have an anchovy fillet that's less than 70 millimeters is less, right? And that makes sense because when we're taking samples, we're actually like what we end up with in our sample is influenced by the probabilities of each of those that we're going to get anchovies of any particular size. If we take the mean of it, it sort of reduces that variability. So it ends up means that we'll end up overall, our samples are going to have means that are closer to the true mean. All right, now if we keep doing this, if we're going to do our sigma divided by rho n for our bulk cans, we're going to have 12 over the square root of 144. It's going to equal 1. We're going to get an even skinnier distribution. So now we're going to have our mean is still 75, but our standard deviation is only 1. So we're going to get a real skinny guy. And we're going to have 70 over here. And now our area under our tail is really small. If we keep going for 400, we're going to get 12 divided by root 400. And that equals 12 over 20, which is 0.6. Right, so this one's going to be even skinnier. Not a lot. We go out to 70 again. Well, I didn't draw this very well. It's going to be even smaller distribution area under that curve. So this should be smaller. My sketch is just that. Okay, so if we're going to find areas under the curve based on our sample, right, we're going to set up our normal curve so that it has the standard deviation of that sampling distribution. And so these are all going to be much skinnier. Okay. So let me show you a problem where we're going to find the probability of something from one of our sampling distributions. Let me get a fresh whiteboard. So here is a typical problem that you would get for sampling distribution of the sample mean. Okay, so average diastolic blood pressure in women in the US is 100 millimeters of mercury. All right, so when we say average blah, blah, blah is, and we have a measurement that's something that we know we can get on hundreds of thousands, if not millions of people, we're going to use this as our mu. We have enough samples that we kind of use it as the true population mean. Similarly, we know it has a standard deviation. we're going to use this as sigma equals 16 millimeters of mercury. If we define high blood pressure as greater than 80, what is the probability of women having high blood pressure in a sample of 250 women? All right. So how do we know that we're going to invoke the central limit theorem here? That's because we have this language in a sample of something, something. Okay, so if it isn't written out in the problem, where you want to start working on any kind of problem is by identifying and writing down what variables you've been given. So let's start with that. What are our variables we've been given? Okay, we've been given mu is 100 millimeters of mercury. Its standard deviation is 16 millimeters of mercury. The cutoff value, or the value that we want to find a probability of, right? What's the probability of women having high blood pressure? Well, how do we know what high blood pressure is? Well, I've given you how it's defined. So the probability we're interested in is x is greater than 80. Right, so we have to figure out what that x is going to be. Specific value, we're looking for an area to the left or the right of. And then we have a sample of 250 women. So every time you see the sample, you're going to want to think little. So little n is your sample size. All right, and we want to know, right, so we have our population distribution our graph here. Now we know we've taken a sample, okay? So we want to figure out what the samples, the sigma over root n is, because we're going to be using that in our calculations, right? So if we do sigma over root n, we're going to get 16 divided by the square root of 250. Oops, it looks like I didn't calculate this out as a separate step. Okay, so that's what our standard deviation is going to be. And we've got this value along our x-axis, 80, and we want to know what this area is going to be. All right, so remember that the normal distribution curve, normal distribution table always shows us the area to the left, so we're going to need to do a 1 minus. No, find this. Okay, so we're going to use our equation z equals x minus mu to convert this to our standard normal distribution, so we can find that probability using our data table. And we're going to, because we have a sample, we've identified it in our problem, we know we're going to use this equation. All right, so we want to find this value, what it's equivalent to on our standard normal tables. If we make that calculation, we're going to get minus 19.8. Okay, minus 19.8. All right, so this drawing turns out not super great. It should be much peakier than that. And it actually is way, way out here. Way, way out there. Okay. And so if you remember off the top of your head that our standard normal table ends at minus 0.0002, then we're going to myself a little clear space here. We're going to see that minus 19.8 is less than minus 3.49. So that means our probability is less than the smallest one on the table, 0.002. Now that's the area to the left. We want the area to the right. So we have to do 1 minus 0.0002, and that's 0.9998. Right, so the answer we're looking for, what's the probability of women having high blood pressure in our sample of 250 women? The answer to that is 99.98% of them. So almost 100% of our women are going to have high blood pressure. If we look at a sample of 250 women. All right, that's a little shocking. All right, so it comes from the power of having the much narrower normal distribution because of invoking the central limit theorem. So when I say invoking the central limit theorem, I mean we've taken a sample so we can divide the sigma by the root n. Okay, so this doesn't seem very interesting or exciting, but when we start the second half of the semester, what we're going to do, because we still don't know what the true population standard deviation is. All right, so we'll find out how this problem was solved by the invention of the t-distribution. All right, so the t-distribution is going to tell us the probabilities, not based on the normal distribution, but based on a distribution that we can use with the sample standard deviation instead of the population standard deviation, because we can't know that population standard deviation. And we need to be able to do this kind of calculation using the actual sample standard deviation. Okay, so the only tricky part of doing these problems is just recognizing that you've been given a sample size in problem. It's just like any old find the area under the normal curve problem, but you just need to realize that you need to substitute in the sigma over root n. Okay, and we're going to get a lot of these answers that they're off of our chart. Okay, so when we have values that are much larger or much smaller than the values at the far edges of our normal distribution table, all we can do is say that they're less than 0.0002 or that they're greater than 0.9998. right? So just less than or greater than is all that we could do in those cases. All right, and that will be the correct answer. All right, I hope this helped. And you will have some practice problems for this on your worksheet this week.